For 200 years, mathematicians stared at a number and could not say what kind of number it was. The number is called zeta of 3. It is defined by a sum so simple that a high school student can compute it. 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed, on and on forever. The value is approximately 1.2020569. The decimal expansion looks completely random, but every mathematician believed, with no proof, that zeta of 3 was irrational, that it could not be written as a simple fraction. For 2 centuries, this remained a belief. Leonhard Euler proved that zeta of 2 equals pi squared over 6. Beautiful, famous, proven irrational because pi is irrational. For odd values of the zeta function, zeta of 3, zeta of 5, zeta of 7, Euler computed numerical values but found no formula, no proof of irrationality, no connection to pi or e or any other established irrational. Just a stubborn number that looked random and refused to confess. Then in 1978, a 61-year-old mathematician working in Caen, France, who had never been considered one of the great minds of his generation, walked into a conference and announced that he had proved zeta of 3 is irrational. His name was Roger Apéry. The mathematical community refused to believe him. Wow! Step back. Bernhard Riemann's zeta function is the most important object in analytic number theory. For real numbers s greater than 1, it is defined by the sum zeta of s equals 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so on. When s is 2, Euler proved in 1734 that the sum converges to pi squared over 6, about 1.644, irrational because pi squared is irrational. When s is 4, the sum converges to pi to the 4th over 90, about 1.082, also irrational. When s is 6, 8, 10, any even integer, Euler found closed formulas involving powers of pi, all irrational. But for odd integers, 3, 5, 7, 9, Euler tried. He computed values, he looked for patterns, he found nothing, no closed form, no connection to pi. Zeta of 3 is approximately 1.2020569. We can compute it to any precision we want. We can verify numerically that it is not equal to any small simple fraction. But for 200 years, that was all. A number that looked random, a number that nobody could prove was even irrational. To prove a number is irrational, you essentially need to rule out every fraction. But there are infinitely many fractions. You cannot check them all. So instead, you use a deeper structural argument. The standard tool is approximation. If you can show that a number is very well approximated by rationals, strangely well, in a precise sense, then by a classical theorem of Dirichlet, the number must be irrational. Specifically, if you can find a sequence of rationals Pn over Qn with the property that the absolute difference between Pn over Qn and alpha is smaller than 1 over Qn to the power 1 plus delta for some positive delta, then alpha is irrational. The intuition, rationals can only approximate other rationals to roughly 1 over Qn. If alpha is being approximated faster than that, alpha cannot itself be rational. For pi, Lambert in 1768 found the irrationality argument by analyzing the continued fraction of the tangent function. For e, Euler and Hermite used integral representations and orthogonal polynomials. For algebraic numbers, Liouville in 1844 gave a general criterion, but for zeta of 3, no one knew where to find a sequence of fast approximating rationals. The standard methods do not produce them. That is the wall every mathematician hit, until Apéry climbed over it. What Apéry did was build, from scratch, a sequence of rational numbers that approximate zeta of 3 faster than any classical method had produced. He defined 2 sequences, capital A sub n and capital B sub n. Both are explicit. Both are defined by combinatorial sums involving binomial coefficients. A sub n equals the sum from k equals 0 to n of n choose k squared times n plus k choose k squared. b sub n equals the same sum, but each term is multiplied by an additional rational quantity that involves harmonic number-style fractions. These are concrete numbers. You can compute a sub 1, a sub 2, a sub 3 by hand. They grow rapidly. A sub 1 is 5, a sub 2 is 73, a sub 3 is 1445. Then Apéry's miracle. The ratio b sub n over a sub n is a rational number, and it converges to zeta of 3 at a specific rate. Specifically, the absolute difference between b sub n over a sub n and zeta of 3 is bounded above by a constant times c to the minus n, where c is a specific number bigger than the asymptotic growth rate of a sub n raised to a careful power. In other words, the approximations are good enough, by a hair, to satisfy Dirichlet's irrationality criterion. How did Apéry find these sequences? He started from an accelerated series representation of zeta of 3. The original series, 1 over n cubed, converges slowly. Each term shrinks like 1 over n cubed. To get k digits of accuracy, you need about n equal to 10 to the k over 3 terms. Apéry rediscovered, or independently found, a much faster series. Zeta of 3 equals 5 halves times the sum from n equals 1 to infinity of negative 1 to the n plus 1, divided by n cubed times 2n choose n. This series converges exponentially fast. Each term is roughly 4 times smaller than the previous. To compute zeta of 3 to 10,000 digits, you only need a few thousand terms. The fast convergence is the seed of the irrationality proof. Apéry showed that the partial sums of this series, scaled appropriately, are exactly the rationals a sub n over b sub n. The combinatorial structure of the binomial coefficients, multiplied through, gives integer numerators and denominators that grow at controlled rates. Apéry then proved, using just elementary calculus and clever divisibility arguments, that this controlled growth is fast enough to force irrationality. The proof, when written out, fits in less than 10 pages. No deep machinery, no abstract algebra, just sums, binomial coefficients, and one outrageously good identity. When Apéry first presented his proof, in June 1978 at a conference in Marseille, the audience was openly hostile. Apéry was not a well-known mathematician. He had spent his career in Caen, a regional university. He had published modestly. He had not previously worked on irrationality questions. His presentation was, by all accounts, chaotic. He stated identities without proof. He skipped over crucial steps. He made jokes. He seemed to be claiming a result that, if true, would be the most surprising number-theoretic achievement of the decade, using methods so elementary they could have been found 2 centuries earlier. The reaction was disbelief. Some attendees stormed out. Others openly accused Apéry of fabricating identities. But 2 attendees, Henri Cohen and the Dutch number theorist Alfred van der Poorten, took notes. After the conference, they sat down to check Apéry's claims. They verified the identities numerically on a computer. They reconstructed the missing steps. They confirmed that every claim Apéry had made was true. Within months, the mathematical community accepted the result. The theorem is now called Apéry's theorem. The proof is taught in graduate number theory courses. The accelerated series, the recurrence relations, the clever divisibility arguments, all of it works, exactly as Apéry said. For Kinde. Apéry's theorem covers zeta of 3. It does not cover zeta of 5, zeta of 7, zeta of 9, or any other specific odd value of the zeta function. Despite half a century of intensive work since 1978, we still do not know if zeta of 5 is irrational. We do not know if zeta of 7 is irrational. We do not know if zeta of 9 is irrational. In 2001, Tanguy Revoil proved that infinitely many of the odd zeta values are irrational. That is, somewhere in the sequence zeta of 3, zeta of 5, zeta of 7, zeta of 9, infinitely many of these numbers must be irrational. But we cannot say which. In 2003, Wadim Zudilin proved that at least one of zeta of 5, zeta of 7, zeta of 9, or zeta of 11 is irrational, but we do not know which of those 4 it is. The pattern is familiar. We know existence. We cannot exhibit a witness. We have, in effect, generalized Apéry's miracle into a partial result that creeps slowly forward, century by century, without ever cleanly resolving the original family of questions. Apéry built one bridge. We have not yet built another. Apéry's theorem is a strange jewel in the crown of 20th century number theory. It is technically elementary. The proof uses calculus and combinatorics that any first-year graduate student knows. It does not invoke modular forms, or elliptic curves, or any of the major engines of modern number theory. And yet, for 200 years, nobody before Apéry found it. There is a temptation to think that if a proof is elementary, it must be easy to find. Apéry's theorem is a counterexample to that temptation. Elementary does not mean obvious. Elementary means that the steps, once you know them, are checkable by hand. It does not mean the steps are easy to discover. Roger Apéry died in 1994. He never produced another result of comparable importance. He was, in many ways, a one-theorem mathematician. His theorem, however, will outlast every fashion. As long as zeta of 3 exists and we recognize it as irrational, his name will be attached. The Apéry story is also a lesson about the sociology of mathematics. A surprising claim from an outsider provokes resistance, but mathematics eventually is self-correcting. If the claim is true, somebody will verify it. The verification process is messy. It involves skepticism, reconstruction, and slowly accumulating agreement, but it converges. Apéry stood in front of a hostile room and made a claim that turned out to be exactly correct. The room caught up, the number theory community caught up, the textbooks caught up, and the strangeness of the moment, an unknown 61-year-old proving the irrationality of zeta of 3 with elementary methods, has been preserved as one of the most surprising vignettes in 20th century mathematics. The number is irrational. Apéry was right. The community caught up.